Look inside the hull of any commercial freighter, and you will find a machine that defies human scale. A massive two-stroke marine diesel engine, firing under extreme pressure, generating relentless kinetic force to move tens of thousands of tons across an ocean. To manage that force, these ships are heavily instrumented. They do not lack data. Every second, networks of sensors continuously feed temperature, pressure, and vibration metrics into multi-million-dollar software platforms. For decades, the industry standard for processing this data has been condition-based maintenance, or CBM, software. These systems ingest the sensor data, log historical trends, set upper and lower operating limits, and trigger alarms when those limits are breached. This threshold-based framework served a crucial purpose. It acted as the primary intelligence layer for maritime operations, catching obvious anomalies before they caused catastrophic engine failure. But when we test these systems against the actual complex fault physics of modern maritime machinery, the framework breaks down. Today, traditional CBM systematically fails. The issue is not the physical equipment. The raw sensor hardware is identical, whether a ship uses older software or a modern neural network. The catastrophic failure point lies entirely within the mathematical logic processing that data. This brings us to a precise engineering question. Why do traditional CBM systems, operating with perfect sensor data, demonstrably miss up to 40% of developing engine faults? The gap between legacy software and artificial intelligence cannot be closed by simply tuning the limits. CBM systems suffer from a structural, mathematical blindness to operational context. We can measure this failure exactly. A 2024 study published in MDPI Sensors provided a definitive, direct comparison of fault diagnosis accuracy, testing different mathematical models on identical marine diesel datasets. This table details the results. Traditional signal processing methods failed to diagnose faults in over 40% of cases, but a state-of-the-art multi-attention CNN tested on identical data achieves a near-perfect 99.9%. A 40-point accuracy gap on identical data requires a structural explanation. It stems from how CBM software relies on static, absolute thresholds. A CBM system sets a threshold, this red line. When engine load shifts, temperature spikes past the limit, triggering a false alarm. AI instead learns a dynamic baseline hugging every operating regime. It detects microscopic drifts over time, identifying precursors without crossing absolute limits. By constantly adapting to operating conditions, the neural network dramatically reduces false alarms caused by shifting weather or load changes. Relying on static limits in a highly dynamic mechanical environment mathematically guarantees missed faults and unacceptable operational risk. But accuracy is only half the equation. In maintenance engineering, the ultimate metric is time. This is a PF curve. The downward axis represents condition, mapping the window between detectable fault point P and physical failure point F. Standard software operates down here, generating an alarm at the absolute limit, providing a useless 0 to 2 hour warning. AI temporal sequence models analyze data history to project where it is going. Tracking the degradation trajectory, the AI generates a reliable alert near point P, expanding the prediction horizon to weeks in advance. A 2-hour warning is severe. The shore team is helpless, and the crew must manage an emergency breakdown at sea, often in violent ocean swells. A 200-hour warning changes the entire operational posture. The shore team has a week to route spare parts, coordinate logistics for the next scheduled port call, and ensure zero unplanned downtime. Temporal sequence learning creates the multi-day lead time required to coordinate logistics and act safely, a resource that static CBM software structurally cannot provide. The final architectural limitation of standard CBM software is its single-track mind. It monitors parameters one at a time, treating every sensor as an isolated variable. In real-world marine environments, machine faults do not happen in isolation. They trigger physical chain reactions. Consider a specific mechanical cascade. A fouled heat exchanger elevates temperatures. That increases thermal stress on bearings, which alters lubricating oil viscosity. This single root problem generates overlapping data signatures across completely different sensor types.
Standard single-parameter thresholds fail here, seeing separate variables crossing lines, triggering an avalanche of uncoordinated alarms that confuse the crew. Multi-label classification architectures, like graph attention networks, evaluate all sensor streams simultaneously. They recognize correlated patterns across sensors, untangling overlapping signatures to output one unified alert pointing directly to the root cause. A 2021 study in Ocean Engineering measured this exact capability, proving that diagnosing simultaneous faults is mathematically impossible for single-track threshold systems. Adding more sensors to a traditional CBM system does not create better diagnostics. Under single-parameter logic, more sensors only multiply the confusion. There is a highly valid operational critique of machine learning in engineering. Chief engineers will not, and should not, trust an alert from an opaque, unexplainable mathematical black box. Early AI systems simply spat out binary warnings without providing the physical root cause. This created a massive trust gap between the algorithm and the human operator. Current research closes this gap directly, using explainable AI, specifically through frameworks called SHAP analysis. SHAP analysis transforms the black box, assigning exact contribution scores to sensors driving a prediction. A 2025 bearing fault study clearly showed spectral entropy and impulse factor drove the majority of the AI's prediction weight. This level of feature importance acts as a bridge. It allows human engineers to look at the AI's logic, see which physical forces triggered the alert, and verify the conclusion against their own mechanical knowledge. This transparent data replaces arbitrary engineering thresholds with evidence-based, physically justified intervention criteria. These frameworks provide a transparent, interpretable advisory for the engineering team, turning complex data patterns into actionable maintenance insights. To be clear, traditional CBM software remains entirely valid in specific applications. For simple auxiliary equipment like bilge pumps with highly linear failure modes, simple thresholds do the job. Furthermore, in data-scarce environments like older vessels lacking deep sensor histories, AI models simply cannot be trained. But for modern, high-value commercial shipping, the reality is stark. For main propulsion engines, turbochargers, and complex power systems, the CBM threshold is dead. The quantitative failure of static logic is thoroughly documented. It misses 40% of faults, generates zero useful lead time, and goes completely blind during multivariate cascades. AI fixes the intelligence layer. It adapts to the operational context of the vessel, processes thousands of variables simultaneously, and predicts degradation trajectories days in advance. The shift toward deep learning provides a mathematically sound path to reduce unplanned downtime and meet the rigorous safety requirements of autonomous operations. The hardware is already installed. The data is already flowing. The era of the static threshold